Okay, welcome again. So today we will discuss about this architecture of 8085 microprocessor. So in the previous few lectures, we have built the foundation for this course so that we will be able to now recognize the various blocks in this architecture and what is the role or use of each of these functional modules. Okay. So you've seen that what is a processor, how it works, how when you interface this with the memory, we have a set of buses, address, data, and control bus. What is the use of these, and how we execute the programs, right? So many things we have discussed. I think most of them now they are clear to you. So we will see now to this internal architecture of 8085. So the internal architecture of any microprocessor, it basically decides that how the operations are performed inside the processor. Okay. So, what are the various units which are inside basically this processor? Okay. So later on in the next lectures, we will map this architecture to the pin diagram of this microprocessor. So it is basically 40 pin integrated circuit. So right now I'm not coming to the pin diagram directly because once this architecture is clear to you, so all these input outputs they are just located at some of the pins in the processor. Okay, so let us start with this architecture. So there are many things which are now clear to you or which you know we have discussed so many things about the processors in the previous lectures. So if you come to this block register array first, okay, so we have discussed that there are six general purpose registers. One is B, then C, D, E, H, and L. So all of these registers they are 8-bit registers. So they are accessible to the programmer. They are available to the programmer for programming. Okay, so you can write or read any data from these 8-bit registers. So you can copy data from the memory location to these registers. You can add the two contents of register B with the accumulator and so on. Otherwise, you can use them in pairs. BC register is one pair, DE register is another pair, and HL register is another 16-bit register pair. Okay, so these three registers they are clear to you. Then we have also discussed about this program counter in the last class. So this PC or the program counter, it is a 16-bit register. And what is the purpose of this register? It holds the address of the memory location from which you are going to fetch the next byte. So this we have discussed in detail. Okay. So if any memory location has some address, suppose you have some data in a memory at any address. Okay. Let us suppose the address is at a location of 2050. Okay. And there is some data in this, which it can be any number, it can be any binary 4-bit, 8-bit number. Suppose it is 42H. Okay. So the first thing the processor does is identifies the location of the memory from which you are going to fetch the instruction or the data. Okay, so for that we need a 16-bit address. Okay, the address is of course carried by the address bus, but who holds that 16-bit address? That is basically stored in the program counter. So this is the first step, in fact, what the processor does. Okay, so the program counter is loaded with the 16-bit address of the memory location, which points to the memory location from which you are going to fetch this byte. Okay, similarly, we have another 16-bit register which is called a stack pointer. The stack pointer we have also discussed. It is a 16-bit register which is used to point the stack. Okay, so stack is a separate memory in the your is this separate part in your memory, so which is reserved basically by the programmer. Okay, so you can initialize the top of stack address by loading the address in the stack pointer. Okay, so that is clear to you. Then we have two more things here in this block. One is increment and one is decrement. Okay, I will come to this later. Okay, then now when you perform any when the microprocessor executes any instruction, what it does, first thing, it loads the program counter with the starting address of the program. Okay, now where that address will go. Okay, so let us suppose I take with the example, you have some instruction. Let us suppose you want to move the contents of a register C or A into C. Move C comma A. Okay, so this is the assembly code, assembly language mnemonic. So you have a opcode for this, and let us that opcode is 42H. Okay, so this opcode has to be stored at some memory location, and we assume that okay, this operation code is stored at a location 2050H. Okay, the processor is supposed to do this operation. It has to move the contents of register A into register C. Okay, so it is one instruction, and for this instruction you have no binary code. Okay, and that binary code has to be stored in the memory. So whenever the processor will fetch, decode, and execute this code, it will move the contents of A into C. Okay, so let us see how it is done. What the processor will do, the processor will first load your program counter with a 16-bit address. It means the program counter will be loaded with 2050 in hexadecimal, of course. Okay, so it is a 16-bit address of the memory location from which you are going to fetch the instruction. Okay, now this program counter will place the data, the 16-bit data, on the address bus. Okay, now this is my address bus, so this 16-bit data will go from the program counter on this address bus. Okay, and you can see that now, see, the address bus is divided into two parts. Okay, 8-bit address and another 8-bit address here. So this is the higher order, this is the lower order address. Okay, now again, see, you can see the difference here. Here the address bus, the higher order address or higher order 8 bits, they are represented with A8 to A15, and the lower order address, they are represented by AD7 to AD0. Okay, and you can see this arrow, this is unidirectional, this is bidirectional. It means somehow lower 8 bits, they are used to carry the address as well as the data. So that is why you have this multiplexing here. Okay, so you have this representation is AD, so it means it stands for address as well as the data. Similarly, AD0, AD1, AD2 up to AD7. So the lower 8 bits, they comprise of the address as well as the data bus. But at a time, it can be used either to carry the address or it can be used to carry the data. So that is controlled by the processor. Okay, that for which time or for which clock time period it should be used for address, for which time it should be used for data. I will go into a bit detail in this, how it is done by the processor. So you have a 8085 processor. Okay, so you have 16 you can say lines which carry the address as well as the data. Okay, so the higher 8 bits, that is A8 to A15, okay, they are used for address only. Okay, it means they will be permanently connected to the decoder that we are using now for this memory address decoding. Now these 8-bit lines, the lower 8 bits, that is AD0 to AD7, they carry the address as well as the data. Okay, so during the earlier parts or during the earlier portions when the instruction is being fetched, they carry the address. Okay, during the next part of the instruction, when the instruction is fetched, they are used, when the memory is basically located, they are used to carry the data. Okay, now since they are used to carry the address and data both, so this address has to be latched. Okay, so use a latch here. Okay, The output of this latch, now these are my higher order bit lines A8 to A15. So you basically separate these 8 bits on a separate lines. So you have A7 to A0. Okay. So I have omitted this terminology now D here because now it is only for address. Okay. So you have a latch here. You know what is a latch. Okay. It is basically nothing but a set of flip-flops. Okay. Maybe D flip-flop. So in the D flip-flop, if you have a D flip-flop, so whatever is in input, same is the output. Okay. Of course, this has to be activated by some clock signal. Okay. This has to be activated some. So whenever the clock signal is activated, whatever is your input, that comes to the output in case of D flip-flop. Okay. This is what is the purpose of latch. It means whatever is the data on these 8 lines A, D0 to A7. So whenever this latch gets enabled, the input of this will come at the output, and you can use now these for the address, not this. Okay. So AD0 to AD7, these are not supposed to be connected to the memory directly. You have to latch this address, or you have to separate the address using a latch, which has to be enabled by the processor. And to enable this latch, you will see in the microprocessor there is a special pin which is called as address latch enable, ALE pin. Okay. So this is in this block, timing and control, ALE. Okay. This is called as address latch enable. So this is a pin on the microprocessor, and this pin is basically connected with the chip select pin of this latch. Okay. This is chip select pin, or it may be named anything depending upon the type of IC that you are using. Okay. So you have integrated circuit here, which is a latch with 8 inputs and 8 outputs. So whenever this latch gets enabled, whatever is the data on the input, that comes at the output. Now this output is basically used for lower bit 8 address. Okay. So higher bits, of course, they are same, but the lower bits has to be latched. So this pin ALE, which is active high pin, this is basically connected to the enable pin or chip select or enable pin of this latch. So this is a pin which is maybe enable pin. Okay. It means, you know, since your address latch enable is active high pin, so it should remain at logic 0. Okay. So when the processor places the address on this address bus, okay, it means suppose if 2050 is my address, so your higher 8-bit data, that is 20H, will be placed on this bus, and your 50 will be placed on lower 8 bits. Okay. And then the processor will activate this signal ALE, address latch enable. Okay. So as the processor will activate this signal, it means it goes from 0 to 1, logic 0 to 1. This latch gets enabled, and this lower 8-bit address now comes at the output. Okay. Now this will again, so once your ALE goes high, after some time it goes from high to low. Okay. And unless and until it again goes high, this address will now remain on these lines. Okay. So this is how we have separated 20 and 50. So this A8 to A15, this will now carry 20, the higher 8-bit address, and your A0 to A7, this will now carry 50H. Okay. And this will identify your memory location 2050H. Okay. Now of course these 8 bits, they are also used to carry the data. So this is a data bus now here. From this your data will come, or on this data will also go. Okay, because it is multiplex now. So the same 8 bits they are used for address, the same 8 bits they are used to carry data. But when it has to be used for address, it cannot be used for data. So that is controlled by the processor using address latch enable. So during the initial clock, in fact at the first clock cycle, when you see the timing diagrams, The lower 8-bit address is latched, and now these 8 bits, they are free to carry the data in the next cycles. Okay, so now see, move c comma a, I am using this as example. So the program counter will be loaded with 2050. This address or this 8-bit number will go on the address bus in two parts, lower 8 bits and higher 8 bits. Okay, and at the same time the processor will activate this ALE signal address latch enable, so your lower 8 bits they are latched. Okay, and this at 16-bit address will go to this memory location. Okay, so your memory location is identified 2050. Okay, now what is the next step? Whatever is the operation code or 8-bit data here, you have to bring this data inside the processor. Okay, it means once the location is identified, the next step is what? Now your processor will generate a control signal. And what is that? Since you're reading the instruction, so it will activate a control signal, that is read. Okay, so this is read is again another pin on the microprocessor. Okay, and it is active low pin, you can see. It means normally it is at logic 1. Okay, so whenever you have to read a byte from the memory, you have to make this high to low. So it goes from high to low. So when this read signal, it goes from high to low, this memory chip will be selected. Okay, and since you have already identified the memory location using the address, so this 42H will be now placed on the data bus. Okay, so this 42H number will come from this location through data bus. Okay, of course the lower 8 bits, because the lower 8 bits now they are used to carry the data. Okay, so this 42H will be placed on this data bus, and where it will go? It has to go to the instruction register. Okay, because it's an instruction, so it has to be, the processor will understand, okay, what is the meaning of this byte or this operation code, then only it will execute. Okay, for that it has to go to the instruction register, then followed by the instruction decoder. Okay, how it will go, through which path? So this 42H is now placed on this lower 8 bits AD0 to AD7, because they are used to carry the address bus, and it will not go in this way. Okay, this will go through a 8-bit address bus, which is in now internal. There is internal 8-bit data bus which is used to carry the data which is fetched from this memory. So this 42H will come like this. It will go from this, connected to the internal data bus, and it will go to this instruction register. Okay, which is 8-bit register now. Now since it is an instruction, so it will go to the instruction register, and the instruction register will release this data to the instruction decoder. Now at the instruction decoder, it will decide that what has to be done. Okay, now since it is a operation code for moving the contents of accumulator into register, see what this instruction decoder will do. When it will decode the instruction, it will give a signal to the timing and control unit. Now this timing and control unit is very important in this microprocessor, because it generates all the timing and the control signals necessary to activate any logic circuit. Okay, so it acts like the brain, human brain. Okay, so you do some actions using hands, using foot, using your body or facial expression, but who controls that? That is done by mind. So your brain sends some neural signals to do all these activities. Okay, so right now I am moving the pen on this whiteboard, so of course my hands are doing it, but how they are controlled? They're controlled from the brain. Okay, so timing and control circuit is very, it plays a very major role in this architecture. Okay, so whatever instruction is coming from this memory, it goes through this data bus to the instruction register. The instruction register decodes it. sorry, it sends this 8-bit opcode to the instruction decoder. The instruction decoder decodes it, and accordingly your timing and control signal will generate certain control signals to activate certain logic circuits which will perform that operation. Now what is in this case? In case of move C comma A, the opcode is suppose 42H. So we have taken this, we have fetched this byte from this memory to the instruction register and to the instruction decoder. Now what the instruction decoder will do? It will activate this control and, or it will inform basically the control and timing circuit. What this timing and control circuit will do? This will copy the contents of register C into register, sorry, register A into register C. Okay. So whatever are the contents in this register A, which is your accumulator, so they will be transferred to register C again through this internal data bus. Okay. So this timing and control signal will send a signal to the accumulator, and it will ask the accumulator to place its data on the database, internal database. Okay, and then it will send a control signal, of course, to register C that there is some data on this database. Please get it. Okay, so this data will be copied from A to C. Right. This is how it is done. Or it may be possible that accumulator sends this signal to a temporary register, and from temporary register it will be given to this C. Okay. So again, see in this block, you will see this register array block. You have a register select. It is also a sort of decoding. Okay, so that is also controlled by this timing and control unit, because you have to select one of these registers: B, C, D, E, H, L, stack pointer, program counter, W, and Z that we have not discussed so far. Okay, so that register selection is also done by the timing and control unit. Okay, and of course there is a sort of multiplexing. Okay, so multiplexing means, see, all these 8-bit registers, they are multiplexed. The data can come to the data bus either from register W or Z or B or C at a time. Okay, because they all share the same data bus. Okay, so which register will be used? So that is controlled by this register select, and which is basically controlled by sending control signals from this timing and control circuit. Okay, so I hope this is clear how these instructions are fetched, they are decoded, and they are executed. Okay, as far as what we have discussed till now. Let us take one more example for the same. Suppose you have instruction add B. Okay, and for this you have some opcode. Let us suppose that opcode is 72H. Okay, so this 72H is now stored at some memory location. Okay, so how the processor will fetch, decode, and execute this instruction? So the first thing it will do, it will place the address of that memory location where this byte or this opcode is located on the program counter. Okay, your PC will hold the starting address. The contents of the PC, they will be placed on the address bus in higher 8 bits and the lower 8 bits. Your AL will be enabled by the processor. Your lower 8 bits, they are latched. Your location is identified. So once the location is identified, the processor will send a control signal read. Okay, and the byte or the opcode or at that particular location is now placed on the data bus. Okay, it will go through data bus inside the instruction register. The instruction register will decode it, and it will come to know that okay, it has to find the addition of two numbers, one is in A and one is in B. So it will inform the timing and the control circuit about what has to be done. Now the timing and control unit will generate control signals. It will send a signal to A, it will send a signal to B, because the data of A and B has to be added. Okay, now see, the addition has to be done in this unit, that is arithmetic and logic unit. Okay, so as in the previous class I also discussed that in ALU you have now two operands, and one of these operands is always fixed. Okay, so one input is fixed, it is always data from the accumulator. The second data can come from anywhere. and you must have some register to store that data, and that is stored basically in a temporary register, which is a 8-bit register. Okay, so like in this case, in case of add b, when the instruction opcode is decoded by this decoder, and the timing and control signal will send control signals to the different blocks. So it will send a signal to the accumulator that will release your 8-bit data. Okay, so this 8-bit data will come from here. It will send a control signal to register B to place the data on this data bus. Okay, so this register is selected, the data of register B will be placed on the 8-bit internal bus, and it will go inside the temporary register. Okay, and then this temporary register and the accumulator, the inputs of these two, they will be added, and your output will be generated, which is again given back to the accumulator. This is what is done in the arithmetic operations. Okay, so the contents of register A will be added to the contents of temporary register, which basically holds the data of B. So A plus B, they are added, and the result is again given back to the accumulator through the internal data 8-bit data bus. Okay, and then there is flags. So we have 5 flags that we have already discussed. So we have sign flag, carry flag, zero, parity, and auxiliary carry. So this accumulator, this ALU, it will be basically also sending the signals to the flags. Okay, it means depending upon the results of that arithmetic or logic operation in the ALU or in the accumulator, so these flags are set or reset to show the status of the results. Okay, so if there is carry generated after some arithmetic operation, your carry flag is set. The result is 0, your 0 flag is set. Similarly, sign, parity, and auxiliary carry. So we have discussed about the flags in the last class in detail. Okay, now one thing you can see here that if you see that the flags, if you see the buses, directions of this buses, this is a bidirectional bus. Okay, it means ALU can read some data into the flag. It can also write some data from these flags. Okay, and this is generally done like, see, when you add two 8-bit numbers, if you add two 8-bit numbers and the numbers are suppose, let us suppose one number is 10001100, another number is, this is suppose number in A. Okay, in register A you have this number, and then register B, it holds a data 11000001. Okay, so when this addition will be done in by the ALU, you will get output as 1 0 1 plus 0 1 1 plus 0 1 0 0 1 1 plus 1 0, and we'll get a carry of 1. Okay, so in this operation, now this 8-bit number will be stored in accumulator after addition, of course, and the carry will be set. Okay, now if you want to suppose add 3-bit numbers, okay, so after add B, if you want to suppose write add C, so it will add the contents of B with A with of course A plus B is gone into A, then you have to add again with C. Okay, now since there is already a carry which generated from the previous addition, so you must take into account that carry also, otherwise your result will be wrong. Okay, so there is an instruction which is used for add with carry. Okay, so if there is any previous carry which is generated, so that is also taken into the picture. Okay, so in that case, this ALU must be able to get the status of the carry flag. So that is why this directional, these flags is, this is bidirectional. Okay, so ALU can set the flags, it can also read the status of the flags. Otherwise, you could see most of the signals, they are unidirectional. So data can come from temporary register to accumulator, it can come from A to this inputs output. Okay, so I hope these blocks, whatever we have discussed, now they are clear to you. So this increment and decrement, if you see here, increment and decrement address latch, what basically it is used to, we have discussed when you load the program counter with the starting address. Okay, So it places the address on the address bus. Your address is identified. Now once the address is identified, the work of PC is over for that location. Okay. Then you generate a read signal, control signal. The data will be placed on the data bus. It will come inside the processor, given to the instruction decoder. It will understand what is the meaning of that code, and it will execute. Okay. So by the time when it is decoding and executing the instruction, the contents of the PC has to be incremented by 1 because it has now to fetch the next memory location. Okay. It has to fetch the next byte which is stored at the next location, that is 2051H. Okay. So automatically the contents of PC will be incremented by 1. Okay. Similarly, once this memory location is identified, it will be incremented by 1 to the next and so on. Okay. So that is what is done by the increment and decrement. Okay. So decrement you can use in stack pointers. Okay. So then there are some other blocks in this architecture. Of course, I will not go into the details of these because it will make you somehow maybe confusing. But on all these blocks we have a separate chapter. Okay, like suppose if you see this interrupt control. So in the interrupt control you have 5 types of interrupts. Of course, we have a dedicated pin for each of these on your 8085 microprocessor. Okay, so that is why I have said that when you map this architecture to the pin diagram, so for every signal you have a pin on this microprocessor. So INTR interrupt. See, in this you can see you have inputs. This is input. This is output. Okay, this is going out. This is also input. This is also input. This is also input. Okay, and trap. This must. I think this needs to be like this. Okay, there may be some error in this diagram. So this is also input. Okay, this is not like this. This is also input. So these are 5 interrupts. Okay, so interrupts, when we use interrupts, basically if the processor is doing some operation, it is executing a program and some other device, okay, it requests the processor to do some operations. In that case we give a interrupt. It is externally, you can say, initiated signal. Okay, so there are different types of operations that I will discuss in the next lecture. So one of those is externally initiated operations. So they are initiated by some other device which is outside the processor. So they are inputs or outputs. Okay, so you have 5 types of interrupts. INTR, which is a normal interrupt. Then you have trap, RST 6.5 or 7.5 or 5.5. These are also called as the restart instructions. So out of these 5 instructions, these 4 instructions, they are called as vectored interrupts. We call them as vectored interrupts. Okay, because whenever the processor is interrupted by sending a interrupt signal on these pins, the program, whatever the processor will be doing, it will stop it. Okay, and the program will be jumped to a particular location in the memory which is called as interrupt service routine. So at that location we have a service routine, interrupt service routine, which is written. So the processor will execute that service routine, and after executing that it will come back to the main program from where it has left. Okay, so we have fixed location for trap, RST 7.7, 6.5 and 5.5. Okay, and then there are some priorities among them. That trap is the highest priority, or it is called as non-maskable interrupt. Means whenever the interrupt on this pin will come, the processor has to service it. It cannot ignore. Okay, otherwise these rest of these interrupts, they are maskable. Okay, it means you can program the processor like this whether to respond to these interrupts or not. So if it is not important, you can just ignore it. But if there is some emergency service that has to be connected to the trap, I suppose I have a simple example I can give you. If there is a processor which is used to execute any task and suppose you have some fire sensor which is connected to this, the output of which is connected to this trap. Okay, it means whenever there is a fire in the building, of course that is an emergency situation. So the processor has to service that request. Whatever it is doing, it is not too much important from that emergency situation. Okay, so such signals you can sensors you can connect to this pin, which has to be processed at top priority. Okay, so of course we will discuss about these blocks in detail. Similarly, you have one more block here, serial control. So you have two pins on the processor which are used for serial communication. So serial input data SID and serial output data. So this is of course, as the arrow indicates. So you can transfer the data serially through this pin. You can receive the data serially through this pin. So serial means one bit at a time. Okay, so there is a serial communication. And then apart from this, now in the timing and the control unit, you have several other signals. So we will discuss them in detail. You have two pins X1 and X2, which are used to connect external crystal oscillator to the processor. Okay, then you have two pins for power supply, 5 volt and one pin for ground. So this is pin number 40, in fact, in your IC. This is, I think, pin number 20. Similarly, you have some other pins. So read and write is a very familiar that you know. Okay, ALE we have just described. Similarly, you have one pin IO oblique. So this is used to identify whether this is a input output or it is a memory related operation. Okay. Then you have reset pin, which is also input pin. So and it is active low pin. It means whenever a logic 0 is applied to this processor, it will be reset. Okay. All the operations will be suspended and its program counter will be reset to 0000 location, starting memory address. Okay. So this is in this. I hope I have described this architecture in a very recent way and with some examples. So we can, in fact, we will discuss this, and when we discuss the pin diagram, I will continue from this part also. Okay, so that we will revise this again because it is a very important topic, the understanding the architecture. And I request you to maybe to watch this video more than once so that the concepts they will come clear to you. Okay, thank you.